You're not talking yet, are you, Brett?
Righto, can you hear me? Sorry. I've just been waffling on for 5 minutes and I've been wondering why no one's writing in the chat box. Okay. Hello, everyone. How we going, boys and girls? The meeting's already started, so we'll keep going with that. How's everyone's weekend, and is everyone okay with assessment 1, your demolition? We all right with that? Could I get some comments in the chat box? How you been going? I know the boys from Wollongong have said they've done it. All good there. How's Maria and Nara? Nara, you boys and girls going all right? All done. Nearly ready to see it. Okay. Why did that do that? Okay. Could you please let us know how you're going with assessment 1? We're going to open up assessment 2 for materials tomorrow. I'm going to chat about it tomorrow. I've got a couple of things I'm going to waffle on about. Firstly, apologies to Nara. I'm not going to get there this week. Could you please chat to Forksy? He's there every Monday night. And go and check your learner portal and check in your Moodle site about assessments that still need to be complete. Daniel and George, I'm going to get you to organise with Forksy a day, and I'm going to come down for a day. So could you give us a ring tomorrow or Wednesday? Anyone else in Nowra, have a chat to Forksy about organising a time. Maria, if you've got anything outstanding, can you send us a Moodle message? Because I'm going to be down there in a couple of weeks. And also I'm going to Wagga and Griffith in a couple of weeks. So I'll give you some more dates tomorrow. All right. Besides that, you probably don't really need me to come down. I'm just doing it as a courtesy and like to finish off the year because it's been such a good year. And, you know, I haven't even seen some of the Griffith students face to face. So I'd like to actually see you and say good day. But in saying that, can you please go to your portal and check it? I've just gone through and I've looked at the on-site cluster, and there's some assessments that I think it's like 3 or 4 times back and forth, and it's so minor. It's just like, please sort it out. It's killing us as assessors. Yeah. Now I have to close the on-site cluster. I'm going to leave it open for 1 more week just because Gleno started on assessment 5. Frank's back, and we're just going to start sweeping through and tidying a few bits and pieces up. Is that okay, everyone? I'm happy with that. Can I get some comments in the chat box? All right. It should be up there, Callum. It should be up there now, mate, I would say. Learning activities. Let's have a look. All right, if you need something open, let us know. I'm going to scroll down. See, you need to be over 90%. Like if there's a couple of bits and pieces that aren't done, okay, that's fine. I'm just scrolling down because I really don't like showing other students, but just so you get the gist of it, this is what we do. We go down and we look at the end of the year and we check, right? Then we also go into someone's their access for their work, just solely them, and then we open up some of the learning activities and have a go at this. This is an example of a student who submitted something that went green. Okay, so calculating live loads worksheet, they've just actually submitted the document and not done the work. All right, now that's great. The thing is, it goes green, but that doesn't actually mean that we know it looks green, but we still go in and check it. Yeah, does that make sense? And see those calculations. They're questions that'll be at the end of the year. So if you've done it, you're going to have a very good understanding and you're going to probably kill the test within a couple of hours. Those that haven't, you're going to be going, oh my God, it's green, but now I don't know how to do the quiz. Does that make sense, everyone? Okay, so we actually see that. Yeah, those are the things that I know a couple of years ago, a student didn't, he had to come back. All right. The reason why we're doing it is because we want you to have an understanding for it. It's going to be open book. Yeah. So you're going to have everything ready to go. Those that are doing the work, you probably kill the test. You just go through and go, oh, yeah, I understand that. And that's the whole reason behind it. Okay. So please be mindful of your learning activities. All right. Your progress bar, which is part of your learning activities, and Adrian's going to be taking over tonight. Are there any questions, boys and girls? Because I'm really starting to sweep behind. I have started sending people messages, but I'm not getting anything in reply. Like, there's an issue with WHS, and like, I need those people just to sort it out. All right. Thank you, Adrian. Thanks, everyone. Please give me a message, and I'll send some more information to the Nowra guys in the next week or two. Okay. Thanks, everyone. Thanks, Adrian.
Thanks a lot for that, Brett. Just checking my sound here. I can hear that you can all hear okay. Just going to grab the desktop, share my desktop here. Make sure that's all working. Just make sure while this is coming up that you've ticked the attendance. That's all open and should be working. Did it work okay? That's working all good. So check your attendance, make sure that you've been ticked off there. And excuse me, I'm going to go through tonight. It's quite an interesting one, actually. It's good to finally be at a stage where we can actually put some nuts and bolts into these structures and make it all come into something that you find on your engineer's details when you finally get your house plan. So tonight, I'm just going to give you a quick scroll through as to what we're going to do, and then I'll open things up throughout the night and you'll get a good idea of where we're headed with it. So we're going to have a look at how houses used to be built and some of the things there. We're going to look at some of the modern houses, how they're built and how we have to work around being able to get enough bracing and things. Tonight's lesson is pretty much about wind classifications and being able to design the bracing and having a little bit of an understanding of how to design the tie downs for a building as well. So we'll just make a little adjustment here on the side. So pretty much we're going to become quite familiar with Australian Standard 4055 and Australian Standard 1684. We're going to have a little bit of a look at masonry walls and some of the hazards with those as they are being built. We're going to have an quiz activity here for you to do with wind loads, some short answer question, and then we're going to go down and look a little bit at the implications of where we build in the world or in Australia particularly, and what implication that has for us in regards to our building site and how we design our homes and things like that, the influence that has had on buildings. We're going to look at some videos on how to classify wind loads, some quick calculations, some helps calculators and things that are able to do this type of work for us. We're going to determine from a plan some wind classification and speeds. We're going to look at some uplift forces, and there's another activity where we've got some short answer question based on some little sketches that we'll give you. And so tonight we've got quite a few things I'm going to open here. I'm going to make available to you an actual calculation sheet that you can save into a file somewhere and get ready for when you're doing the quizzes for this unit. So at the end of the night, we will have done a few quizzes. We'll look particularly at cyclones and some cyclone damage. I'll show you some information on some of the damages from Cyclone Yasi, I think it was, and a few others that we may have to be aware of if we build in some areas that are north of us. So what I would encourage you to do, if you want to make it real quick and easy for yourself for the quiz, is set yourself up a little folder somewhere. You can see I've called this particular one Structures Cluster, and I would set yourself up a little folder somewhere on your computer for information that'll help you with your exam tips. So I think someone else has grabbed the screen here. That's not me there. I think I'll just grab that again. Here we go. So set yourself up a little folder where that you can find quickly and easily for when you come to do your exam, and you can right click anywhere in the white space when you're in a folder and then just get yourself a new folder, and I would be calling that exam resources or something like that. And that's where I would put my Australian standards. I've got all my Australian standards here, so you need to make sure that those Australian standards are active and they're not coming up as a green screen like that, ready for when you go to use them. And I would also put in there any little cheat sheets that you might have. I've got some cheat sheets. Here's one here, for example. I'm going to give you this sheet tonight, and I'd be putting something like that in there because it goes through step by step how we can do our bracing and all those sorts of things. And if you've got that handy and you get a question like this in the exam, which you will, then you're able to quite quickly just use the calculations from the exam question with the exercises that you've got and be able to make it into something sensible. Now I notice, oh, okay, so Brett, thanks for answering that question. Basically, there's a restriction will come up as soon as you, if you download an Australian standard, because they're designed to be the most up-to-date that they can be. And so if you just download them as a straight PDF document from the website, then they're going to go green after a couple of days. If you look back at a few activities we looked at earlier, we said you can sometimes bypass that by printing the document to a PDF. And I think most people have been having some success doing that. Just click on print. Instead of sending it to your printer, just send it to Adobe PDF or Microsoft Print to PDF. Most people have that on their computers, and then you'll be able to save it as a document that'll be useful for you. So tonight, what I want to talk to you about is I'm going to open up a picture for you, and I want you to type into the chat box and tell me who lives in a house like this. So with this particular house that we're looking at, coming up here on this picture in a second, is a typical, I would call that a fibro type house. There's heaps and heaps of those in suburbs, probably built around the 60s, 50s, maybe 40s, post-World War II. Lots of people coming back to Australia needed, probably built by A.V. Jennings or some of those companies. And so with a house like that, you can see that we had sheets of material that were put on the side of the house, and the joins in those sheets were covered by strips, and those sheets were potentially asbestos type sheets. But you can see with a building like that it's got reasonably small windows. Possibly if it was built in the south of Australia or in the north of Australia, it may have had a bit of insulation in it. It's got vents you can see up in the top corner here, which makes it quite breezy. That would be full of asbestos on all the eaves lining and also the walls of that building. There's probably been no insulation underneath the building. And you've got a building that has awnings because it did get quite hot in summer. But if you look at a building like that and you imagine the floor plan, we've got across the front here, we don't have a lot of room for bracing of the wall, but down the side here, we've got heaps of room for bracing because there's only looks like one tiny window and there is a chimney that chops through there, but you could get a 45-degree brace from that back corner there of that building right through to the probably down here to the front, possibly coming underneath that window, and that you'd get a really good brace in there. You've got enough room on the left-hand side of that window, the right-hand side of the window, between the window and the door, possibly, certainly on the right-hand side of this window to be able to get some good bracing. And we'd be able to get enough bracing in a building like that with those small windows so that we could actually meet the requirements for being able to build that building strong. I've opened that up for you. And so I'm going to go now and look at what's happened these days. People didn't like living in houses like that because they wanted something that was more, that was much more able to be, actually I've got to go to a different website for this one. And I think I had that. Okay, so I'll set up this particular one. This activity, you're probably going to need to go to a, oh no, it might work on this one. It wouldn't work on Chrome before. So this particular website here, we're going to go and have a look at a typical house that you might find these days. So I'll show you the picture of the house first. I'll open each of these so you can have a quick look at it. And then we'll go for a walk through this house, and we're going to try and identify how hard it is for us to be able to put bracing on a building like this. So look at the house that they build these days. How much room have we got on the side of the window there and here for bracing? It's all garage across the front. If I show you the floor plan of that house, pretty much what we've got there is a building that has room down the side here. Potentially there's 2 lots of bracing we could put in there. We might fit a little bit in here. We might fit some bracing through here. There's not much room in here because unusually that does have a little bit of walling. Usually that's quite open on modern homes. We might fit some bracing down here. We might be able to fit a little bit of bracing in here, but then we're right inside the building, which can make it hard to stabilize the side of it. If we think about this building, the wind potentially can come from, we allow for it to come from two different directions across the building, either from the left or from the right, or we plan for it to come from down this part of the building or from the front of the building. And so we have to put be able to put enough bracing in there to be able to resist the forces of the actual wind that's blowing against it. Now we're going to calculate tonight what the kilonewton forces potentially could be for a particular site somewhere in Australia of our choosing, so that we can design how much bracing we need on that particular building. But if you look at that building, it's quite different to the previous one that I showed you. With this one here, we've got lots and lots of spots where there's room for us to be able to put bracing. This one here, we don't have many spots at all. Look out the back here, that's all so open plan there. How are we going to brace that from the wind coming against us this way? We've got a wall here we could potentially use, and a wall over this side. Potentially that wall in there could be a bracing wall, but then, you know, it's quite hard for us to brace some of these types of buildings. So that's one of the problems that we have when we have a building that's built like this. So let's have a little walk through this building and have a look at what she looks like. If you look around in this building, you can see that there's really not much wall space here. This one beside the garage, maybe. We come back into this building, this room a little bit, and this is thanks to Hotondo. You can see on their home side here, Hotondo Homes. So there's not much room on the left-hand side of that window. In fact, a lot of bracing we're going to learn tonight can have a minimum of, we have to have a minimum of 900 millimeters, and there's probably neither of those sides of the window have 900 millimeters. Let's have a look in the front bedroom and see how much room we've got. So there's probably not going to get 900 millimeters there. We may on this side, maybe not. We've got plenty of room on this side for some bracing up and down that wall. So we'll come back out here and have a look down towards the back of the room. And you can see with the modern houses that are built these days, it can be quite an engineering problem to be able to get some structural strength for wall bracing. Most of this is just windows. We might have a little bit of room here on the left. There's not much there. We'll duck in here and have a little look out the back part there. You can see we've got a little tiny bit. The problem with that wall that's in there, if we step back here and have a look, the problem with putting bracing on this wall in here is how are we going to tie that in to all the roof trusses and everything else, and make that wall or that part of the wall, even though it's not really long enough that side, but it might be on this side. How are we going to make that strong enough so that it can resist the forces of the wind blowing in from on the other side of that back wall? That can be quite hard to do. You can see we do have a wall here which we could use for bracing to resist this wall from being blown back towards us. And if you go into even the bedrooms, they still have huge windows in the bedrooms these days. So people just like to have so much window space that we often have to adjust the standards to be able to suit. There's not much room there. That might be 900 if you're lucky, so you might get some bracing in there. You definitely got some bracing across the back, so when the wind blows against this window coming across from left to right, we could use that wall for bracing. But if we go in here a little bit further, you'll see we might be able to use that wall there for some bracing if we're lucky. But we start to get complications because on the other side of that wall, there's going to be another room. And if we put a sheet of plywood brace on that wall, then how are we going to treat the 20 mil thickness of the plywood brace when it sits next to the rest of the studs? How are we going to make all that blend in without there being a dip in the sheets? And so what people can sometimes do is they will put packing on some of the studs so that they're able to fit the ply in. Because if you just put a bit of plywood across part of that wall to be able to achieve your bracing, then what about the rest of the wall? Because that plywood sticks out 20 mil or so when you put it on the wall. So you can see it makes it quite hard on a modern building to be able to put that in there. We've got one window at the back. Now this window is an interesting one because potentially if that window can move, if it's not too close on this corner, we may be able to run a brace from that top corner, because bracing always has to attach to the top plate and the bottom plate. We may be able to run a brace from that top corner down, sneak it underneath the building here and come underneath the corner of the window and match it up to the bottom plate. But bracing can't go too steep. there's an angle that bracing is allowed to go into, and that would be, that's in Australian Standard 1684, and it'll tell us what the angle is that we're allowed to work on. And so we've got all these things that we've got to keep in mind as we start working our way through buildings these days. So you can see that's an example of that particular building and how bracing can be quite hard to fit. Now I've put a little example up here for you and what I want to show you from this one, if you fire that up and have a look, is that's that floor plan, and I've grabbed the green texture there, and any wind that comes down from the top of the screen down to towards the bottom, or from the bottom of the screen to the top, I've said if the wind is coming from the top to the bottom or bottom to top, then the fat green lines represent the bracing that's required to be able to resist that wind force. And looking at that just quickly without taking measurements or things, they're spots where we may be able to put some bracing. Okay, they're the walls that are long enough to be able to put some bracing. Now this wall out here is probably brick, so it may not count quite so much. These walls here where I've drawn circles on the end, that means that we're going to have to consider that wall. There could be some complications, because as you know, I'm sure, when we build a wall, we normally have a gap of 20-30 millimeters to the bottom chord of the truss, and there's two types of methods of fastening the bottom chords of trusses onto the top plate of a house. One particular method is where we just use a simple L bracket, and there's a lot of movement between the bottom chord of the truss and the top plate of the wall frame. And that wouldn't be suitable having a real strong wall frame here that can resist all the forces, but then the trusses can move a little bit because you've only got L brackets on them. The trusses would go across left to right. You'd have an L bracket here and that could move. So what we would have to do is on that wall there and this wall here, we would have to treat the bottom chord of the truss differently, and it would be the type of method in Australian Standard 4440, which is designed to attach the truss or the trusses onto a braced wall. That would be called a braced wall, and potentially then we could use that wall as a braced wall to be able to hold the roof and everything, but we may need then to be able to fasten maybe even some plywood sheeting underneath the bottom chords so that when the wind blows against this edge here, the trusses aren't going to bow in. There's all sorts of complications and things that we can have. And then if we look at the second lot of bracing that we have to plan for with this job, we would have to, I might be able to fit that all on one page. We'd have to plan that so that, for example, if the wind is blowing from left to right or right to left, these yellow walls here potentially could be the braced walls. Now, you're not allowed to have all of your bracing down one end of the house and none down the other and say, oh, that's enough bracing. You can't go more than a certain distance without having some bracing. So this is quite a long distance here. And if we're to look back at the floor plan, I don't know whether it's got measurements in there, but if we look back at the floor plan for this particular house, no, there's no measurements in there. So we don't know how long that is or how much bracing we might need. And so that could mean that we have to do something special here, because we can't have good bracing here and a bit of bracing here and a big gap in between. That could leave this part of the house weak and subjected to failure and things like that. So can you see that the situation that we're up against is a chapter in the Australian Standard that's quite complex, and there's lots and lots of different directions we can go when we come to looking at wall bracing. Just going to increase the zoom on this once again, bring it back up to 100. So I'm going to show you the next item in what we're looking at here tonight. Actually, some of this. Oh, this is the brief history of Australian Standard 1684. I'll just make that available to you all so you can see that. So here's a brief history of Australian Standard 1684. And anything to do with timber framing of a certain size timber framing, we can pretty much go to Australian Standard 1684 to find out things for. And it's only going to be certain size buildings, and it's buildings that are this size. This is 1684. That building there is okay, that you can see on the front there. If we look at Australian Standard 1684, this is the type of building that we can work on. We'll bring it up to speed here. It's going to be a building of those sizes. So 3 metre maximum walls, 35-degree pitch, 16 metres maximum width of the building. So 16 metres is maximum. And then that pretty much gives us the footprint of the building that's 1684 is going to cover. What happens if it's outside of that? Then we've got to get an engineer to specifically design it using the knowledge that they've done. Remember, engineers will go to uni for 4 years minimum to learn full time, to learn how to do these sorts of things. So we're doing a course 3 nights a week, for a month and a half. There's no way we're going to know what they know. So we're just teaching you how to read the documents that those people can produce. And you can see here, in around the 70s, we had small rooms, small openings and windows, plenty of room for bracing. In post-war and through to the 70s. Then we had the light timber framing code, slab on ground construction, roof trusses, open plan design. In the 80s, we had bracing and tie downs. Now back around the late 70s and 80s, we didn't have the books like we have now, timber framing code, but we had some guidance booklets and documentation. And back in 1992, I've got the first book that they brought out in 1992, Australian Standard. It's a bit tattery now, but they started producing those as a book. And then when the internet came in, and in solidly around the after the 90s, in the 2000s, they started producing it as an online version. That's where we can get it from now. So it changes from time to time, and we need to make sure that we get the latest update when we come to the getting our Australian Standard, and that's where we get the information from, and it's real comprehensive. And we're going to have a bit of a look at it tonight from the point, and actually do some practical exercises in how to work out bracing. So I'm just going to show you this next section here. What I want to do here is discuss the procedure for wall bracing, Australian Standard 1684, and tie downs. And I just want to touch on it briefly when we look at it. So you can use that link to be able to go to your Australian Standards, or you can go right to the top of the page where we've got a link. I find this one works really good, just takes me straight to it, but you should have somewhere there 1684, and you should have somewhere where you can quickly access it. And if you save it as a print version, you probably won't have the bookmarks on the side, but you can access quite quickly the parts to do with bracing and anything that we're going to be dealing with. We're going to be dealing with section 9. Now, I'm just going to quickly give you an overview so you know how it works. There's section 9 where it starts. That's page 110 out of 277 pages. So we're right through. Basically, if you go through this book, it's following it from the start of a building after a couple of chapters of introduction right through till the tying down of the building. And pretty much you need to skim through this before you do your exams. Just skim through this and make sure that you've got an understanding of where you find things. So this pretty much is going to tell us, if you look at the headings here, of some of the different systems, and then we come to things like temporary bracing. You can almost guarantee that that particular information right there is going to be an exam question. And the point there is that 60% of the final bracing that we will calculate tonight as being required to hold a building up needs to be in place at the end of each night when you go home, once you start standing walls. So anything that could fall over, 60% of the final bracing that would require needs to be in place to be able to hold it. Okay, that's what the requirement is there. And when we look at wall and subfloor bracing, this part here is probably the best thing you could refer to, and I've put it on the activity for tonight so that you can see, because it's going to go step by step exactly what you do to be able to work out what your bracing requirements are. It says bracing shall be designed and provided for each story of the house and for the subfloor where required in accordance with the following procedure. First thing you do is determine the wind classification. Then you determine the wind pressure. Then you determine the area of elevation, and you calculate the raking force. We haven't even looked at bracing yet. What we do by calculating the raking force is we work out how much pressure is actually going to go against the building in the particular chosen direction. And when we know how much pressure is against the building, then we can go searching for a bracing system to be, in our case for walls, to be able to resist that force that we found out that we needed when we did our calculations. Okay, so D and E is where we spend our time. We do whatever we can to be able to get to D, which gives us a reading I'll show you what the reading looks like. So clause 8.3.4, and just go down here till we get to 8.3.4. Here we are. This is what we're aiming for. And the reading we're going to come up with is going to look like this. It's going to look like one of these numbers here. Okay. Just check here, pressure, kilopascals. So we're going to come up with a reading, and the reading is done by, there's little calculations and things as we go through. Actually, that's the raking force, that 8.3.4, and we'll eventually come back to this chart up here once we get the raking force. Where'd that chart go? Up here. So calculate the raking force, clause 8.3.4. That'll give us a kilonewtons force. And then once we get the kilonewtons force, we can go searching down on our table for finding some bracing that'll be able to give us the strength that we need. And there's a table in here which gives us all of that. We disregard subfloor bracing for us because you're going to have enough of a struggle working out. We'll work hard enough just working out the wall bracing for this one. So just want to introduce you, before we get into wind loads and things, a little bit about masonry walls and construction. And there's been some news items about this. Did that open up? There's been some news items about this lately, and so we just want to have a quick look at this and see some of the issues that can come from dangers of masonry walls and construction. Here I am in SafeWork New South Wales. You can see this is legitimate information from safeworknewsouthwales.gov.au, and this was a couple of years ago. It was in the news. There was a masonry wall that fell over and killed someone. Recently, one worker died and another was seriously injured in separate wall collapses in Sydney construction sites. And so they say here, some of the contributing factors were wind, reduced mortar strength in the walls, damp coarse membranes providing a line of weakness. Some of the actions prior to need to ensure the stability of masonry walls during construction or demolition work, because masonry walls can be used as bracing and things like that too. So that's why we're touching on this here. It's important to, if you're going to use this as a bracing wall, to make sure that it's strong. So what has to happen is 60% of the strength of the wall needs to be ensured or braced up for when you walk out each night before you leave it. And you can see that there's quite a bit of information here for masonry walls prior to construction, identifying walls that will need temporary support. That's the key, is temporary support until they achieve their full strength. Sequence construction, so that masonry walls are constructed at a time when there's cross walls and there's not too many people around. Limiting the height of each lift to avoid overloading green masonry, things like that. So I'm going to leave that available for you there. And then I've put up here a guide that SafeWork printed and produced as a result of that problem with the masonry structural walls, bracing walls, and they've made this available to us, and here's your guide here. So this, you can download the whole guide if you want to, but pretty much let's have a quick look at what this guide says. So introduction, plan and prepare, identify the hazards, assess the risk, control the risks, establish the no-go zones. So with the no-go zones, that's where nobody should go, as far as having areas where you can see here, ensure that any no-go zone extends at right angles to the wall on both sides, at least a distance equivalent to the total supported wall height plus 1.2 metres. If winds exceed fresh winds, establish a no-go zone. Okay, so there'll be a table there, and this is pretty much a click-through document, which will help people to be able to identify how to make sure that any masonry walls that are being used, particularly in relation to bracing and relation to construction, will have some controls in place so that people don't get injured. Pretty much the rule is with most local government councils that anything that goes above 1.5 metres high will need some sort of approval or engineering design, because it can be pretty dangerous, anything that's too high. If it's only real low, it's not too bad, but if it gets too high, then it can be a problem. Now, I'm going to make available to you this Build Right activity, which we've become a little bit familiar with as we've been working through this set of units. There's quite a bit of information here that's fairly introductory in relation to bracing. And so this particular one talks about things that we're already familiar with. You can see there we talk about different wind loads, the effects of forces. We've spent a little bit of time on this, different types of bracing systems. And pretty much this is what we're trying to do, is put a brace in place on a building to be able to resist the wind force. And we only work on two directions on the building, working on the narrow end of the building from both ends, and we treat the worst case scenario, which in this case would be this end of the building, and that's the one we plan our bracing for. And then coming across from this side of the building, that's the other case. Now, why would the wind coming in from the left side of this building be worse than the wind coming in from the right-hand end of the building? Do you want to just type into the chat box and we'll for tonight, and tell us why you think the wind force would be greater blowing on a gable end than it would be on a hip? Thanks, Tim. Which one of those two types of roof construction would give you the greatest force? And Josh has hit it on the head. There's more surface area on the end of that building with the gable end than what there is on the hip end. Okay. In fact, that hip provides a little bit of downwards force, which is we calculate when we're going to calculate that tonight. You can see there's an example of that there. We can see that all vertical surface, so this is the worst wind direction here. Look at how they've placed a bracing wall in the middle of this end of the building so that stops it from bowing in. So that's an example. If you can't do that because the building is way too open plan on the end here, you might have to place a flat sheet of bracing across on the ceiling, or make the roof such a structure that it can hold the top of the wall. The bottom of the wall is held because it's fastened down to the slab or the floor, but the top of that wall may need some bracing, and that's where they might put some flat bracing in there. Then we've got our permanent bracing, and you can see examples of that. And one of the considerations with permanent bracing is maintaining wall surfaces ready for sheeting. And then the other bracing there we talk about is temporary bracing, and you can see there's an example of temporary bracing, and then nominal wall bracing. And so for nominal wall bracing, I'm pretty much just going to take you straight to the Australian standard, where we talk about nominal wall bracing. I'll just duck straight back up to, let's just go quickly to where it is. So I'm at the beginning of this chapter. I'm just going to do a Control F for search and type in nominal. And let's find some hits for this word where we want to stick with our, here we go. And here's nominal wall bracing. So we have two types of wall bracing. Okay. Walls shall be permanently braced to resist horizontal raking forces applied to the wall. Wall bracing shall be designed to resist raking forces to or greater than the forces calculated from clause 3.4. The two types of wall bracing are either nominal wall bracing, which is the wall lining material with sheet material such as plywood, plasterboard, fibre cement, hardboard, or similar materials. That's called nominal, and you're allowed up to 50% of the total bracing that's required for a building to be achieved from nominal wall bracing. Structural wall bracing is the other type of wall bracing that we're allowed. Somewhere there's that 50%. The maximum amount that can be resisted by nominal wall bracing is 50% of the total raking forces as determined by clause 8.3.4. So this is the key thing. What I want you to get into your head right now is we've got two types of bracing that we can resist all those wind forces from. One's nominal, which is normally the plasterboard or the fibre cement sheet that you're going to put onto the building. Okay, if it's an internal wall, your nominal bracing, you're allowed to calculate for plasterboard, fibre cement sheet, or things like that. If it's an internal wall that's sheeted both sides, you're allowed to have 70.75 kilonewtons for every metre of wall. If it's only sheeted on one side, you're allowed 0.45 kilonewtons for every metre of wall. So let's put this into example here. If we knew what the length of that wall was there, this wall running through here, let's say that's a 4 metre wall. It's a reasonable little house, this one. Probably more like 3 metres actually, because it's a probably going to have a 3 by 4 bedroom there. So if that's if that's a 3 metre wall, we're allowed 3 times 0.75 for that wall in nominal bracing. Let's see what that comes to, just so you can see how this works. So 3 times 0.75, that's going to give us 2.25 kilonewtons of bracing right there from that wall. There's only one thing we have to remember though, and I'm just going to try and see if I can see it here before we go too far. I'll tell you about it, and then maybe you can find it and tell us. The minimum, two things actually. The minimum length that we can claim for bracing in nominal is 450. And the other thing to remember is if we're claiming nominal bracing on a particular wall, like this one here, for example, we can't then go and slap some structural bracing on and claim structural bracing plus nominal bracing. You got to choose either one of the other. Somewhere there it says that, and I just can't think where it is at the moment, but somewhere in here it says you can't have structural and nominal. You've got to make a decision, which one do you want? Obviously you choose the one that's going to give you the most. So if you can't get a structural bracing that's more than 0.75 per metre or 0.45 per metre, then you'll go use your nominal. In most cases structural is going to give you more than that per metre. So structural wall bracing is spoken about here, and that's the majority of the job. And here's an example you can see here. Look, even the simplest structural bracing, which is 2 diagonally opposed timber or metal angle braces, consisting of 45 by 19 millimetre hardwood timber bracing fixed to each stud and plate with 150 by 2.8 millimetre diameter galvanised flathead nail. If you do that with a minimum of 1800, you've achieved 0.8 kilonewtons per metre. So if you've got 1.8 metre and it's 0.8, let's do the math on that. 1.8, because that's a minimum you can have, times 0.8. You're already going to be higher than the other one. If you go 1.8 times the 0.75, you're going to be better off to go with something like this. So in pretty much all cases, you're better off to go structural if you have a choice of structural or nominal. But the good news is we can actually use nominal for some areas where we don't want to get structural. So this one here, we'd probably go nominal. And with this building, you'd probably find that these engineer designers have used nominal for all these internal walls here, maybe even that one, maybe not, and these internal walls, and they're able to allocate that as a part of a bracing member for the building. Now, if they're using this one here, they're going to have fix the trusses to it. If they're using some of these ones here, then they could be fine for adding to the bracing requirement that we need for that particular job. So that's an example of how that works. Let's just move on to our first little completion activity that we can do here. We're going to do a quick wind load calculation. I've got a little bit to do tonight, so pretty much what you're going to do is use the plan that's supplied and you can actually answer those questions. So I've already had a bit of a look at this one. I'll just pop that into another screen. I'm going to let you work on that yourselves while you're listening to me in the background. If you do that, just look up every now and then, and I'll try and highlight with you what's real important for you, so you can just stop doing your quiz and jump onto having a look at what's real important. So if you look at this one, it says what is the wind load rate on the leeward wall of this plan. So leeward is over on this side, and what is the wind load rate, and you've got to go through and do the calculation there. So it's not too bad really. It's just get a calculator and go 5 plus 3, that's 8, minus 5 brings you back to 3, and minus the 3. You're just going to work your way through there until you come up with your answer. We did have some example calculations of that earlier. You have to actually work out the area of that wall and work out the roof areas and things like that, so that you're able to come up with your calculation and you can work your way through those activities. And all of these questions, there's about 4 of them I think they're all just relating to that little sketch that you can see there. So I'm going to let you just keep working on that. If you're all good with that, I should have left that little heading open. So what I want to do now is actually go to an example of some wind regions and show you how we come up with one of the first things that we need to come up with on the Australian standard, which is what's going to be our wind rating. As soon as you start looking on these charts, one of the first things that you come up with, go back to the beginning of chapter 8 here, one of the first things that you have to be able to do, you can see here, step 1 is determine the wind classification. And we can gain that from Australian Standard 4055, okay, or New Zealand Standard 1170. It's got a repeat of the information in there. So we have to actually determine a wind classification. And then we work in from there. So this, a fair bit of tonight is actually going to be about wind classification. And to do that, we need to have a site somewhere in the world where we can do it. So I've opened this up for you, and I think that's going to open up a little introduction to that. You remember this little chart that I've showed you a few times already before, and that's Australia. You can see there's your different regions in Australia based on the wind. So each of these little sections here is based on the strength of the potential strength of the wind in Australia, and we choose our region, anything through from our seas, okay, being the most severe, back to our A's being the least severe. And we follow a little process where we talk about where we finally come up with a wind rating. Now, one of the things I just want to bring up with you, because we have that chart there, we've got that map of Australia, which is the very first thing we're going to come across as soon as we start to look at Australian Standard 4055. Is I want to talk to you just briefly about longitude and latitude and the implications that this has on the siting of a house and the building of a site, and the building of a house and things like that. So the thing here is that ultimately the Earth has been divided up into 360 degrees and then broken up into minutes and seconds and things underneath those degrees, but basically 360 degrees. And it all starts from where you can just see a picture there of the right-hand side of England. If you go over to Europe on that map, and you can just see I've got the little pointer there just on the left, on the right-hand side of England. Can anybody type into their chat pod the town in England where the Meridians of Longitude start from? Let's see who knows that one, who the smarty pants is, who understands that one. Yes, good on you, Callum. It's Greenwich. So Greenwich is where somewhere years ago they decided where they were going to start this from, and it all came from 300, 400, 500 years ago, when people like Magellan and other people used to learn to sail, and they needed navigation, and it ended up with what we have today. So originally, boats and trade would only occur when the wind blew in certain directions. So when they wanted to trade from the majority of the known world around to Asia and the rest of the world, they'd wait till the time of the year when the wind blew that way, and they'd head off that way, and then they'd come back the other way when the winds changed. Eventually they learnt to tack on sailboats, and so they could go wherever they wanted to, and eventually Magellan headed off and divided the world up into 360 degrees and other people, and now we have what we call these vertical lines, which are meridians of longitude, and we have the Earth divided up into parallel lines, which are parallels of latitude. Now you can remember, you're probably not going to need to remember this ever again, but meridians of longitude and parallels of latitude, I always remember it because I think of pallet, and pallet is PA for parallels and lat for latitude. So I remember parallels of latitude, and they run parallel right around the Earth's surface. And if you think about where they are, that determines pretty much how a lot of houses are built, and because the closer to the equator, the less need for heating a house in winter, the more need for breezes to come into the house in summer, and the more comfortable we can have our houses if we just keep the sun off the house. And so you can see here we're divided up pretty much into 90 degrees. Vertical is 90 degrees coming across to the equator's north. And here in Australia, which isn't actually shown on this map, we're down around about 30, 32, 33 degrees. Hobart's about 45 degrees, 42 degrees. Last year I went to Fairbanks in Alaska, which is 64 degrees north of the equator, and just quickly take you there for a quick skim. And there's some things that I noticed, and I noticed that they build the houses a lot differently because of this. So where we live in Australia, we build houses such that if you're over on the coast, we build houses so that we can let the light in let the air through, and try and have as comfortable a house as we can, based on the type of temperature of where we are. So we're just going to skim right out so you can see where this is. Just don't get too dizzy. Hang fire for a second while I set you up for it. So you can see here we are over here in Australia, and most of our the equator's sort of up through here somewhere. Mostly we come down here around these regions where I showed you the high winds start from, sort of Port Macquarie, Coffs Harbour, that area north, Geraldton over in West Australia, and anywhere on the coast it follows up there. And we need to design houses so that they let the air in, but they're also really, really strong so they don't blow apart, because we get such bad winds. Down around the coasts around here we can get bad winds, but inland it's not quite so severe and so bad. And once we start getting south, this is probably 30 degrees here. This is probably 40, maybe 40. That's probably 30. I think Hobart's about 35 or 6 or something or other. Then we get cold winters, and we can get warmish summers. But the biggest thing we're trying to do is keep the houses warm and try and be energy efficient with our warmth. When we get up around Alaska, where they only have snow for 9 months of the year, pretty much what we need to make sure we've done there is we've built a house that can withstand the extreme temperatures. So they actually test their houses to make sure there's no leaks. They'll put a big pump inside the house, and they'll put a gauge on it, and they'll make sure that they can pump the house up with air and that it doesn't leak over a certain time period. It loses a certain amount of pressure, and it's an airtight house. We don't even worry about that much down here, although it may become more common as time goes on. And if you look at when they build up here, they actually get so cold up in some of these areas that they put heaters in the driveways. And you can see that that's basically 9 months of the year that's going to be covered in snow. And so we have to build a lot differently. Up there, they have sun for basically 24 hours a day. So when we were up there last year, 11 o'clock at night, you could read a book outside. It was just so bright. So they have to build houses a lot differently in some of those areas. And so longitude and latitude has a lot to do with where we build a house and the type of house we build. That's why that's why they build houses like this. And lots of times they were really, really uncomfortable houses to build in. And then along comes builders these days where we build houses a bit more like this. And all of these houses have to be built to the codes and to the standards. And the standards have been designed so that they match the type of areas where buildings are going to be built. Okay, so I'm going to just show you a quick extract here from Australian Standard 4055. I think that's going to open up. And you can see here that the classification is for wind loads in buildings based geographically, and also where it is in the street is based on 10 different classifications. And we talked about this the other night. We've got N 1 to 6 and then C 1 to 4, and we could think of the C as being cyclone. So I'm going to show a video now and play a video based on wind classification, and we're going to get stuck into actually classifying the wind on some buildings after this, and I'll go through and get you set up so that you're able to actually look at a plan and classify and work out the type of wind loading that's going to occur on it. So I'll just turn the microphone off. This video goes for a couple of minutes, and when that's finished, just type in the chat box and let us know you're finished, and we'll jump back into it again. Okay, it looks like most people are done fairly well there. That was quite complex, and I think very few people will probably follow that just from a video. But why we've got that there is you're going to need to refer back to that, and it's going to mean more and more and more to you as we go through the rest of the presentation here, and as you start doing this yourself. What I said to the guys here when we were watching that video, it's real important that you have a look at how he had set that out. And I'll just quickly set it up. I don't know whether I can actually show you. You can see basically how he set that up. He's had himself on hand some specific information. He's had an address in Australia, a street address in Australia. He's had a topographic map. He's had a printout of it so he can put a text mark around the page and draw lines and take measurements so that maps to scale, and he's able to work out slopes of hills and things, and then he's got the Australian standard to be able to work it through from there. So that's the type of thing that we're going to be doing on an actual plan. Just going to quickly show you, just touch on a couple more things before we actually get into it. In this particular example here, this talks about how there's special applications for high wind areas. We have to be careful of that. So there's a part here on 1684 which talks about high wind areas. You can actually read that through. Then there's another one here that talks another extra information just highlighted, which talks about some more explanatory information for additional construction requirements. Each different state have their own requirements, and this one here is where they talk about rigorous testing for metal fatigue, okay, and things like that. Now, the next one here that I'll show you is an example of the pressure on the area of elevation. So we're going to talk about this, but basically one of the things we've got to determine is the wind direction, and it's going to be, we have to work out the pressure on the area of elevation, and this shows you the 10 different wind classifications, and it shows you an example of the pressure. It says they're vertical surfaces, flat walls, gable ends and skillion ends, pressure on area of elevation. And you can just choose this table in this example just as your basic amount that you use, or if you want to fine tune your bracing, you can actually, and you think, oh, there's ours might not have eaves on the right hand side, or it might have smaller eaves, or it might have this, or it might have that. You can actually go through and fine tune it, and you might be able to save a little bit of kilopascals on your pressure there so that you can reduce the amount of bracing that's required. And if you're building a lot of houses, you would probably do that. Otherwise, you would probably use this very first chart that says on all of the different types of houses that are going to be exposed to wind, we're going to choose, we're going to work on the different pressures and things there. So there's examples of that. Now, I'm going to put up just show you a couple of quick things, and I'm realizing a lot of you have just jumped into the quiz and you're probably not listening to anything that I'm saying, but the information is here and you're going to have to come back through and go through it yourself anyway. But I just want to highlight that there's a couple of things that I've put up here that can help you to be able to do this if you get stuck. And I would advise you to use it as a backup. You always use two systems to be able to do these calculations if you can. So quickly go through and check it, or do your calculations on some of these systems like I'm going to show you, and then check it with another system so you can make sure you're right, because you're going to expend some money once you start building a house on the bracing system. And so here's the first one here. This is basically a summary of Australian Standard 4055, and this is a design guide from Stratco. You can see here, that's the old picture of Australia, and you just determine whereabouts you live and where you're going to work on, and you pick a spot there. So it basically says go through and choose the region where you're going to choose in Australia, and then it says choose the terrain category, and there's a summary straight from Australian Standard 4055. It's the same wording and almost the same pictures. Might be probably drawn a little bit differently to avoid copyright issues, but that's pretty much what you do, terrain category. And there's the topographic effect. That's pretty much what it says in Australian Standard 4055. And what I like about some of these documents, which supplement the Australian standards, and you would have to check and see if because they don't get updated like the standards do, you'd have to check and make sure they're still in date. But it gives you a real good graphical presentation of the slope of a building, because the topographic classification determines the effect of wind on a structure due to its location on a hill, ridge or escarpment, and the height of the slope on the hill, ridge or escarpment. Okay, So obviously if it's on the top of the hill, it's going to be a lot stronger than it is on the other side of a hill. I don't know if anybody's ever climbed Pigeon House Mountain or some of those mountains that are over in on the coast that's got a fairly flat top on it. But if it's blowing a gale and you just get over the edge of the mountain, just over on the lee side, you'll find that there's hardly any wind, because that's what happens with escarpments, and that's what this takes into account. The fact that on the way up the hill and certainly on top of the hill, we're going to get a lot of wind. Then you got a little swirling effect right over the hill, and sometimes that's taken into account here. So you've got different choices that we make here. So we put it into a table and it gives us our wind factor. And then shielding is looking at where it is. Is it right beside Lake Illawarra where it's open and the wind can get up a heap of speed across the lake? Or is it hidden down in a little suburb somewhere so it's not going to get any speed? And that little resource that we've put on there is just a real quick, good summary of wind, how to determine your wind classifications. There's also a PowerPoint here that I'm going to make available to you, and that PowerPoint will go through the same type of things. So there's heaps of resources here for you to be able to do your research, because you're going to spend a fair bit of time just going through and doing your classifications. And there's an example of that. I'm not going to spend any time on that now other than just that. And then I want to show you the end result of determining the wind classification. And here's a document that I'm going to make available to you, and this gives you the end result once we work out. We're basically trying to work out our region, and then we're working out our terrain category, we're working out our topography, and we work out our shielding, and then we're able to come through to a classification, in this case C4. And if you did have a need to know what the kilonewtons or the wind speed was, then you could go and work on that. But that information is chosen once you start looking at the documents. So now that's a summary. Oh, there's a summary document here on determining wind speed on this resource. So this one's going to give us a quick overview of summary: wind region, terrain category, topographic shielding. So that's put up there for you. And then the very last thing, which you'll find hopefully quite helpful, you may need Internet Explorer for this one. I'll see if it works on Chrome, possibly not. Oh yeah, it might work. No, it's not going to work. So I'm just going to copy that link and put that across to my Internet Explorer, because here's a little calculator that'll actually do the classifications for you. And like I said, you need to check all of this, because who knows whether Sheds Online's all up to date and taken the latest updates and things, but there are calculators and things that can help you. So obviously if we're in New South Wales, and let's say we're over here somewhere, we can go through and answer the question, select the terrain, and then that'll give us our next choice. So if we're going to select, let's say, for example, this type of terrain, it'll jump through to the next shielding. And this is where we look at our shielding, and we might determine we're in a fairly built up area. We choose that one, and then we select our slope. So you can see this will help you when you look at the Australian standards. There's one choice is average slope of less than one rise in every 10 metres. The steeper one here, what's our steepest slope on this one? Average slope between 1 metre rise in every 5 metres and 1 metre rise in 3 metres. So that looks like that's a steeper one. Let's choose that one. And then we come back and select the site position. Are we located in the lower third of a hill, the middle third, or the top third? So this misses a couple of things. It doesn't get over the top of the hill, but it does come up with a bit of an estimate and a result, and it's suggesting there possibly terrain, region A, terrain 4, shielding 1, slope 4, location 3, comes up with potentially it might be an N3. It's probably said N3 as a worst case because they're protecting themselves a bit, but that's an example of some of the different types of calculators, and you can use that as a bit of a check if you want. So what we're going to do now is I'm actually not going to open up that next quiz just yet. I want to show you a little bit of an example here of on this next video about building in cyclone regions and some of the types of things that they've got to take into account as we realise how serious this is, that we get our wind loadings right. Mike. Andrew's done. Everybody else going all right? A couple of others done. Righto, so obviously that's promoting that particular product, but that's interesting to see what they were saying there. Did you get the bit where they talked about putting the steel rods directly down through into the footings? I did some work on a building in Queensland and that a block of units, and that was one of the first things we had to do. We'd run the threaded rod, this type of thing, run the threaded rod through from the footings all the way up through into the top, and then that ties eventually down into the up into the trusses, and you tighten those things down, and that's not going anywhere. So it's just a different way to build, and that's part of the tie down that's talked about that we need to be aware of. When we look at when we get our bracing sorted out, we also have to take into account our uplift forces, and that's where we're going to be looking at the Chapter 9 in the Timber Framing Code, where it talks about the upload forces, and that's where we're still using these same terms here, the kilopascals, the N ratings, and those things as we come into being able to solve the structural requirements for the building. Another couple of things I'm going to reveal here for you and show you before I show you some scary photos. So this particular one is construction in high wind areas. That's another thing. We have alpine areas and those sorts of things which need to be taken into account. And the intent of building construction in high wind areas to ensure the structure has sufficient strength to transfer wind forces to the ground. To resist these forces, we have to have an anchorage system where the roof is connected to the walls, bracing system, and a continuity of the system and an anchorage all the way down. Just a real quick introduction here to the connection requirements for your buildings. And you can see this is taken here from, it's got a 9 in front of these, everything here, the tables and everything. So that's Chapter 9 from the Australian Standard. It talks about general connection requirements. Have a look at this washer down the bottom here. Anybody ever seen a 5mm thick washer? In this particular case with M16 bolt or coach screw, the washer size is 65 by 65 by 5mm. That's a pretty serious hole down right there. And so drilling for bolts, it's got to be real specific. Bolt holes in unseasoned timber shall be 2mm to 3mm greater than the bolt diameter, and for seasoned timber 1 to 2mm. Okay, so it's pretty specific, and there's no guessing with how you fit everything in together. And then the next thing I'm going to show you here is the prior to connectors and tie down connectors guide. So these manufacturers produce their own guides, and this is just an example of some. This is a 24-page booklet that they've produced, showing you the different types of tie downs they have. Look at them all: truss ties, miter plates. There's ties for anything, and so they'll all have a kilonewton capacity. Okay, they come back to a joint group, which relates to the Australian standards. They'll talk here about Australian standards and things like that, and everything will have a capacity that it relates to. So here's our kilonewton. You're familiar with that term now. That's our kilonewton capacity there. Another quiz I'll show you in a second. First of all, I'll just show you a couple of pictures of some activities and things. So here's our pressure on our elevation, and this is where there's a table that tells us how to work out the pressure. In this particular case, we can go through and choose our pressure based. You'll see this when we look on 4055 and 1684. This shows us the kilopascal pressure based on the size of the building, on things like the roof pitch and all those types of things. So we put all that together, and that's how we come up with it. Now, I want to show you some pictures before I go on to some more of that. Okay, we got a bit there still. I might just looking at the things we had to do here. I've got a picture down the bottom here, which I wanted to show you on Queensland construction. And then we're going to go into a little bit of some more activities there. So in this document, this was a 64-page booklet that Timber Queensland put out, and I had a couple of pages that I wanted to show you here, and this is basically a review of what they put out. It would have been a presentation back in the day from general solutions designed for houses based on some things that have happened in cyclones and different things over the years up there. And there's a couple that I wanted to point out to you. So going to just show you page, I think it was page 42. There's page 42. In this particular case, this shows you an example of how the bracing works. So here comes the wind on the left-hand side, pushes up against the building, not bad down the bottom because the forces just slip straight down onto the slab. Up the top here, they come through to the floor diaphragm if there's a first floor. If it's a two-story building, it comes, some of those forces, half of them will go down the bottom and half of them will go up there, up to the ceiling. And then those forces up in the ceiling will push, and eventually they'll come to a braced wall, which is pinned on the left and the right and fixed on the ceiling up the top there, so that the forces then can transfer back down to here. And then they'll hit the next brace through here and they'll transfer down through to the bottom. And we're always trying to bring the forces down as soon as we can, as safely as we can, down to the floor down the bottom. That's an example of how the bracing works. So we can't have these braces too far into the building. We want to try and get them as close to the edge of the building as we can, so that we can get those forces down towards the bottom as quick as possible. And then the next one I was picked out here to show you was some examples of some buildings here. You might have seen some of these, and I think they may have been from Cyclone Tracy, I'm not sure. But in this particular example, I would suggest that the temporary bracing wasn't 60% of what the permanent bracing should be. And that could be the type of effect, and I'm sure you've seen pictures of things like that. Now, the last bit here is some of these really hit home to us because there's some examples of things not to do. Now, the whole purpose of us doing this structures part of the assignment is partly so you can have a real good understanding of how things work. But one of the reasons is when you get the engineering details that comes with it, either the truss information or whoever gives you engineering details for most of the jobs that you'll deal with, because let's face it, you're not going to do this for most jobs yourselves. So whatever the council has approved as the engineering details, it's important that that's how you build the job. And you can see that putting the nails a certain distance apart on the edge and a certain distance apart in the middle is part of the specifications that will be given to you. That wouldn't be acceptable, somebody punching a hole through the bracing like that, because now we've basically taken that whole section from here across to here out as being potentially useful bracing. This type of thing possibly wouldn't be acceptable, where the hold down bolt has just gone into nowhere. That's not going to be acceptable. In this particular case, obviously the frame was built differently to the slab, and so they've just bolted a big angle across the edge there in this particular picture that they've accessed. What about with garage doors? There's even an Australian standard for garage doors. Okay, normally the garage door installer will be aware of that, but that needs to be taken into account too. So what else was I looking for on this one? I think there's a couple of pictures coming up here showing us some examples of things that might be the main ones there for that one. So that's a little document that's available there for you. It's got some real good useful information in there for you. Now, I want to show you the last video before we've done that one. I just want to show you the last video before I go into some of the activities here. Actually, that's available for you to watch. I'm going to turn that one on, and that pretty much goes through what I'm going to go through in a second. And that's one that Brett's done there that'll pretty much show you how to do the activities that we're going to work on now. So we'll come back up here to what I haven't shown you. We'll show off some of these. In this particular case, we've got the long length of the building. So we've got some Australian standard. There's some pictures that have been put up there for you. I'm going to let you look through these yourselves. I'm going to move straight through to some of the activities for you. That one there, that's the shorthand. Show that one. In this case, I'm just going to open those up for you because you can look back to these if you need to, and basically this will show you how all this works. So in this particular case of this one, that just shows us a G type plywood bracing, and we're able to achieve whatever the kilonewton is shown over on the right hand side here. You can't actually see it there, but that's 3.4. If we do all the things that are suggested on that page there on the Australian standard, then we'll be able to achieve that particular kilonewton of bracing over that area. Now here's an activity that I'm going to open up for you, and I'm going to show you work through my solution quickly with you. And this one you don't need to fill in yourself, but I'm just going to show you quickly, and I'm going to open up the solution one that I work through, and I'm just going to quickly work through this one, because then you've got one that you're going to work on. So you're going to have a student's little plan similar to the one I'm showing you, but just different measurements. And then you're going to do that, and then you're going to upload it. And then you're going to answer the quick questions there. And then I'm going to just show this activity, because that's the last activity that we do there. This one here just shows us an example of strengthened walls for shelter during cyclone times in Northern Territory. And that's an example that you have to have strengthened walls in some of the buildings to be able to give people a place where they can go and hide if there is a big cyclone happening. Now, like we've mentioned to you, you can use Australian Standard 1684 for your tie downs, or you can go to the manufacturer of fasteners, as long as you're doing exactly what they say. And there's an example of what Ramset might have and might show you. And I think that's the last thing. So let's just go through and get ourselves ready for the activity for tonight. Then you're going to do this one here. I'm just going to show you the blank one that you'll be given. In this particular case, you're given 2 questions. This is the first question. Just get this out of the way, and I'll show you the solution to it. So in this particular question, we're given we'll be given a certain amount of information. In this particular case, we're given a wind rating, which is shown here somewhere. It's in your question sheet, and then you'll just run through until you're able to do all the calculations to be able to work out the answers to it all. And I'll just shut that one down, and then I'll open it up on here. I'll work through this one with you. That would have been better if that opened in another. That one there I'll show. I've shown that one there, so you've got it now. This one here would be one that I would save into my file, ready for exam tips, because this is going to go through some bracing, and it's going to go through a little bit of bracing and working out. Once we've been able to work out what our wind loading is, this is going to go through how we can work out our bracing. So in this particular case, this is set out asking you the questions about how to fit your bracing in. This particular case, we've got a bracing plan, which is shown a picture of you here, and we've got step by step how to work this through. And then here's some information in the box over this side. And this pretty much tells you where this comes from. It's told us that we've got a C1 classification, and we're going to actually, first of all, in this first activity here, be working on the long length of the building and working out what bracing we need across the building to resist the wind that's coming against the long length of the building. So I've put in here bracing plan 1 across width of building. So on the wind, if the wind's on the side of the building, we've got a 25-degree hip roof. We've got a C1N2 type wind rating, which has been given to you. We haven't actually calculated that yet. We've got a wall area. In this particular case, we have to know the height of the wall. So the height of the wall has been given to you as 2.7 meters high. Okay. Now you'll find that 2.7 times 8 meters is the length of the building. You can see 8 meters is written in there, the length of the building. And then we come back here and we divide that by 2, because back on Australian Standard 1684, it tells us that for the area of elevation, we only take half the height of the wall. Okay, so we take our wall there and we only take half the height, because the bottom, remember from one of those diagrams I showed you, the force goes down from half of the wall down, it goes down to the floor. So we only have to take half. That's where we divide it up there, and that comes to 10.8 meters squared. So that's the actual area of the top half of that wall where the wind's going to blow. Okay, and then we come back down to our little calculation. Now it's handy to set it out on a chart like this, because it means that we don't forget things as we go through. Now, and that's where I put that note in here for you. Now with the roof area, we take the length of the roof and divide it by the height of the roof. That's as in above the rise of the roof. You might remember from your calculations of roofing that if we know what the slope of the roof is and we know how deep it is to the middle of the roof, then we're able to calculate the rise of the roof. Well, I've put the calculation in here for you. If we work on 25 degrees and go 10, 25 or 25, 10, times it by 2 meters wide, because this building's 4 meters wide, so we're only going 2 meters in. That means we've got a rise of 932 millimeters for the roof height. So if we've got a roof that's 8 meters long and it's and we have to actually take off 932 millimeters because of this reason here, you can see that in this particular case, looking on the short end of the roof, the height of the roof is 930. If it's 4 meters wide, to work out the area of that roof, it's basically all we have to do is basically take we're going to reduce that back to a square. So I'll just pop a square on here to show you what that looks like. So we're going to come in here, and if we halve that again, we're going to end up with we can basically turn that shape into this shape, and then you'll find what we've got is our area of the triangular end of the roof. Okay, so pretty much if you look at the end of the roof, we just on our calculations here, we subtract whatever the height of the roof is, and that allows for the little bit of exposure on that end to come across to here, and it forms it into the surface area of the roof. And I've done that calculation there for you and explain to you why that triangle gets taken into account like that. And then so that's 8 meters minus the rise of the roof times by 0.93, which is times the rise of the roof, because it's not actually 8 meters long of roof, and that gives us our meters squared of exposure to the wind. So if we looked at the side of the building there, that grey part there is 16.38 meters squared. Okay, now we've been told over here to use 1.1 kilopascals as the pressure that's going to occur on that building. So 16.38 times 1.1 is 18.1018 kilonewtons. So on this particular house, 4 meters by 8 meters, we have to have just over 18 kilonewtons of strength for all these cross walls spread evenly throughout that house to be able to resist that wind. Now, we haven't actually done the maths on it here, but I made a note down the bottom for you that 50% of that strength, so that's about 9 kilonewtons, can come from the normal sheeting that would be on that house. So if that was a brick veneer house, we'd have single sheeting on the inside of both those end walls. We'd have double plasterboard there, so we can have 50% of that bracing. That means we would have to allow for 9 kilonewtons of bracing structurally. In this particular example, we're just taking that 18 and we're just looking for a type of bracing that will give us just over 18 kilonewtons of bracing. And in this exercise, what Brett's done with this, and I've worked through with here for you, is that if you look at type G bracing, okay, this is type G bracing. All right, we looked at this a little bit earlier. I'll basically go find that one. Here's our type. Here's our type G bracing. Actually, that's just going to search for way too many things there. We come down here till we find type G bracing. Back up on 8. Type G bracing is plywood or masonite type bracing. Somebody can find the table, they can just type it in. There it is there, I think, actually. I know that's N, G, H, I, J, so back a little tiny bit. There's a type G bracing. So if we use this type of bracing, that's plywood, using all that information that's in that little table there, then we're able to achieve 3.4 kilonewtons for every metre. See, it says over here 3.4 kilonewtons per metre. Now it says here that this type G is a minimum. somewhere here it says what the minimum is. Normally it's 1.8. So if we have a wall height of 2.7 meters high, then we can probably try and find runs on our plan of 2.7. Well, we can, if our sheeting's 900 wide, then we can go 3.4 times 0.9, and if we have a couple of sheets together, we'd be able to achieve a fair bit of bracing there. So what we've got set up on the table here for you is if we can get 3.4 kilonewtons for every metre, we need 18.18 kilonewtons. Divide by 3.4 means we need 5.299 metres of wall that's available in that plan to be able to have some bracing. If we need 5.299 metres, then how do you reckon we'd go on this job? That might be 3 metres there. We might get another 3 metres there. So we might be able to achieve our bracing there. And we might be able to achieve our, because there's no walls on that one there and there. We would need some over this side as well though. So that's an example of how we work it. Okay. So it's real important to remember that 50% of our bracing might be able to be claimed as nominal bracing. And we have to also allow for the fact that sometimes bracing has a minimum length that we can run. So for ply bracing or sheet bracing, it's normally 900. For structural bracing that runs on the diagonal, we have a minimum, and you can see here it lists this particular type of bracing, anything from a minimum of 1800 to a maximum of 2700. And that's been indicated for you in this particular table here where Brett's put in there 1800 to 2700, and this one's in 900 millimeter units. So this can help us to be able to plan how much bracing. This is the end result of us doing all of our work in bracing, and then we have to do the same thing for the wind blowing against the end of the building. This time the bracing is going to be the long way of the building. Okay, so the bracing plan in this particular case for plan 1 is along the length. The bracing is along the length of the building, and the wind is on the end of the building. So we have to do all our calculations based on that. The wall area is going to be 2.7 meters high for the wall, times 4 meters wide, because this building in this example is 4 meters, divide by 2, so we just get the top half of the wall, 5.4, and you can see that an example of how that works. And there's lots of different ones there that comply, because we're only looking for 8.72 kilonewtons in that one. Now, that little example is a real good way for you to be able to do your exercises with you when you do that, the activities here. And I've made both of those available to you, so you can see an example of that there. And what I want to do next is open up your activity for you to do for tonight, and that's an example of pretty much that what I just showed you on the Word document. That's all opened, but you just have to put your own calculations in. So you can see here it is. It's pretty much what I just showed you on the Word document, but you've just got to put your own calculations in. There's your measurement there. In this case, it's 7 meters by 5 meters. Just check every single thing there and make sure that it's all right. So you can't just copy straight from what I gave you. And I would suggest you use that one I gave you and type in the same sort of information as you go. Do all your calculations. So you've got the side of the building, you've got the end of the building, and there's your calculation. So this one here is your bracing plan for the long length of the building. This one's for the short length, and your job's to go through and fill that out based on this one that I've made available for you. Then when you finish that, you can upload it. And then when you finish that, you can do the quick quiz, which won't take you very long. And to do that, now these will be open for a couple of nights, so you're not going to necessarily finish all of this tonight, but work on that and make sure that you upload. Now, do watch out for the people who just upload a blank document. It's going to catch up with you. When we get to the exam at the end, pretty much if you have a completed activity sheet that's done, then that's going to be so much easier for you to be able to go through and do the work quickly for your exam. So you can have access to all this sort of stuff and then be able to work it all out. So I'm just going to see if there's any questions that are coming up here. We are going to open another one of the assessments tomorrow night, but just concentrate on getting some of these things done. way too much to take in. Exactly, Scott. That's why it's recorded. Your brain is going to hurt. That's part of doing exercise will make your muscles hurt. This will make your brain hurt. It is pretty full on, but there's plenty of videos and activities and help there for you. And so just work your way through those, try and get them complete. And we'll actually go through and do some more work on these structures things over the next few weeks. Obviously, you only got 4 weeks left after this week. So you're almost there. Just hang in there and keep getting stuff done. Are there any more questions that I need to address before I shut down here and help the ones in the class? Should the roof end area include overhang? Good question there, Tim. The answer is no, but let me just show you why it shouldn't. Yeah, all the answers that you can possibly ask are in here. So what Tim's asked there with his little question is, should the roof area include overhang? And that was a very good question, Tim. Is relating to the area of the elevation. So if we go right up to our little chart, which you remember you don't want to lose, this tells you step by step what to do. Pretty much, I would say if you only want to remember one thing, then ditch everything and write down 8.3.1. If you can do 8.3.1, you're going to be able to blow wind bracing and tie downs and everything. So the question that Tim's asked is related to point C, which is determine the area of elevation. And to do that, I'm going to just go and show you graphically, Tim, with figure 8.2, where you'll find here we are 8.2. I'm just going to go to the bottom of 8.2, make sure we know what all of 8.2 looks like. And you can see there's 3 8.2s, there's A, B, and C. Now there's a note here that talks about the eaves, and the overhang, which Tim's asked. Basically, the answer is no, we don't allow for it. But I'll just show you where it is here. Here it is. It's probably note 3 on each of these A, B's and C's. It says the area of elevation of the triangular portion of the eaves overhang up to 1 metre wide may be ignored in the determination of the area of elevation. So that little triangle in the end, you don't worry about it. You can see the area of elevation there. Any other quick questions on this? The way I always taught this unit over years and years and years is I would say to somebody, just copy that wording right there and put that into a Word document. So just copy that, put it into a Word document like that. Open yourself up a Word document, and this might help some of you if you're feeling a bit confused. Just stick that into a Word document there and then just go through and do it. Okay. So in this particular case, determine the wind classification. You're going to have to go to 4044 and do that. There's a few videos on that, but I'm going to do a little session on that probably tomorrow night or whenever I can on it. Determine the wind pressure. In that case, you're going to go to 8.3.2 and you're going to do what it says on 8.3.2. Okay. And you just go through and answer it with your plan beside you. Here's 8.3.2, the wind pressure. And it says there, go to table 8.1 to 8.5. 8.1's down here somewhere. Table 8.1 to 8.5, and you'll be able to answer this. So maybe that'll make it a bit easier for you if you're feeling a bit too confused. You just got to go through and follow it step by step, following through that information there. Any other questions? Exams on the 28th, I think, or has there been an adjustment made? Kamal, it's on the last Thursday. Kamal's asked a question there, the exam, that'll be on the last Thursday, which is let's have a look when the last Thursday in November is. That's the 28th. It can't come quick enough, I agree. 28th at 4:30, Andrew Falk said. Stop the recording. Yes, thanks, Glenn. Thank you. Thank you very much for running that, Glenn. Has anyone else got